Good day, everyone. I, William Wallace A. Lamberte, together with my group mates, Ablon Edward John, Urfe Carl Emmanuel, Melancion Kim Ayan, and Velas Adrian Clark, are here to present about or to report about transient response design via gain adjustment. So we already know from the previous videos how to get the root locus and how to sketch a root locus. So now we will be discussing, or we will be presenting another way to get the root locus using transient response design via gain adjustment. So we are given a condition justifying a second order approximation, which are namely, the first one is higher order poles are much further into the left half of the S-plane than the dominant second order pair of poles. The response that results in a higher order poles does not appreciably change the transient response expected from the dominant second order poles. Second is the closed loop zero near the closed loop second order pole pairs are nearly cancelled by the close proximity of higher order closed loop poles. And the third one is closed loop zeros are not cancelled by the close proximity of higher order closed loop poles, are far removed from the closed loop second order pole pair.
So we are now tackling about how to solve our root locus through the transient response design. But we are going to use a different approach of solving through simply adjusting our gain. Now, let's say we have a given root locus and we are to adjust the gain by moving our closed loop poles to a different point on the root locus. And if we move it to a certain point, we will be able to get the desired characteristics, which are the setting time, the peak time, the percent overshoot, and the damping ratio. Now let us first talk about the relationship on our S-plane. If we take a look at our S-plane over there, we have the relationship between our real and complex axis. As you can see in the graph, we are dealing with a constant peak time, which is our horizontal line, which means that it is our imaginary part. Now, we also have our constant settling time, which corresponds to our vertical line. That means that our settling time is dependent on the real part of the pole. Lastly, we have our constant damping ratio, denoted as zeta, which corresponds to our radial line below. Now let us move on to knowing our second order system equations. We talked about wanting to get certain characteristics like peak time, the settling time, and the damping ratio, and also for the percent overshoot. To solve for our peak time, which is denoted by Tp, the formula is Tp is equal to pi over omega n times the square root of 1 minus zeta squared. Now for our settling time, which is denoted by Ts, it is found by using the formula of Ts is equal to 4 all over zeta multiplied by omega sub n. And also for our percent overshoot, it is found by using the formula percent OS is equal to the exponential negative zeta multiplied by pi all over square root of 1 minus zeta squared times 100, where zeta is also equal to cosine theta. Finally, our damping ratio, which is denoted by zeta, may be solved using the formula zeta, which is equal to ln percent overshoot over 100 all over the square root of pi squared plus ln percent overshoot over 100 squared. Summarizing the design procedure for higher order systems. First is to sketch the root locus for the given system. Next is to assume the system is a second order system without any zeros, and then find the gain to meet the transient response specification. Next is to justify your second order assumption by finding the location of all higher order poles and evaluating the fact that they are much farther from the complex axis than the dominant second order pair. Lastly, if the assumptions cannot be justified, your solution will have to be simulated in order to be sure that it meets the transient response specification.
Example 1. We have our equation here. E of s is equals to k times s plus 1.5 divided by s times s plus 1 times s plus 10. Design the value of gain k to yield a 1.52 overshoot. Also, estimate the setting time, peak time, and steady state error. And now I am solving the equation k times s plus 1.5 all over s times s plus 1 times s plus 10. So the first thing to do is to get the poles and the zeros. So for the poles, we have 3 poles, the s plus 1, and the s plus 10. So then the next one is we get the zeros, which is only 1, the s plus 1.5. The next thing we do after getting the poles and the zeros is getting the p minus z, which is p is equal to 3 and z is equal to 1, so p minus z is equal to 2. Next is we get the angle of the equation. So the general formula of the angle of the equation is 2x plus 1 all over p minus z times 180. So we input 0 and 1 to the general formula. So after that, after inputting 2 times 0 plus 1 over all over 2 is equal to 1 half. So 1 half multiplied by 180 is equal to 90 degrees. So that's the first angle. The next one is 2 times 1 plus 1 all over 2 is equal to 3 halves. And 3 halves multiplied by 180 is equal to 270. So 270 degrees. So 270 degrees is our second angle. By that we can get two angles, the 90 and the 270 degrees. After getting the angle of the equation, we then proceed on getting the centroid of the equation using the formula summation of real p, which is the summation of real poles, minus the summation of real z, which is the real zeros, all over p minus z. So we already know that the poles of the equations are 0, -1, and -10, minus the zeros of the equation, which is the negative 1.5. So 0 minus 1 minus 10 minus negative 1.5 all over 2. So 0 minus 1 minus 10 minus negative 5 is negative 9.5 divided by 2. We get 9.5 over 2. So we divide negative 9.5 by 2, we get negative 4.75. After getting the centroid of the equation, we then now proceed on getting the k. So we have a general formula of -1 over g of s. So we can get this by just reciprocating our general equation, which is s plus 1.5 all over s multiplied by s plus 1, and then multiplied again by s plus 10. So by doing this, we can get s times s plus 1 and then multiplied again by s plus 10 all over s plus 1.5. We then use FOIL method to expand the numerator of the equation. So by using FOIL method, we get s cubed plus 11s squared plus 10s all over s plus 1.5. We then derive this equation to get the derivation of k. So we use the formula VDU minus UDV over V squared. So V, which is S plus 1.5, and then the derivation of U, which is 3S squared plus 22S plus 10, minus U, which is S cubed plus 11S squared plus 10S, and the derivation of V, which is only 1, so all over S plus 1.5 squared. We then simplify the numerator. We get 3s cubed plus 22s squared plus 10s plus 4.5s squared plus 33s plus 11 minus s cubed minus 11s squared minus 10 all over s plus 1.5 squared. And then we again simplify the numerator, and then we get the final value 2s cubed plus 15.5s squared plus 33s plus 15 all over s plus 1.5 squared. So the general formula has a negative on it, so we multiply negative 1 to the derived equation. So we get the newly derived equation, negative 2s cubed minus 15.5s squared minus 33s minus 15 all over s plus 1.5 squared. By this, we can now get the roots of the equation, which are, the first root is negative 4.36, second root is negative 2.77, and then the third root is negative 0.627.
In continuation, we will going to find the damping ratio with the following using the following formula, which is negative ln percentage of overshoot over 100 divided by square root of pi squared plus ln percentage of overshoot over 100 squared. So right now our percentage of overshoot is 1.52%. We substitute that on our equation, which will give us a damping ratio of 0.8. With the use of damping ratio, we are going to find our theta. We're going to use our cosine theta is equals to damping ratio. With the use of that, cosine inverse 0.8 is equals to 36.87 degrees. With that, we can now graph our root locus with the zeros and poles. With our pole 0, negative 1 and negative 10, while our zeros is negative 1.5, while our centroid of asymptotes is negative 4.75, discussed on the previous discussion. Now, we will use our percentage overshoot to locate, or with the use of our theta, we're going to graph our the following data. Example: given a unity feedback system that has the forward path transfer function g of s is equals to k over s plus 2 multiplied by s plus 4 multiplied by s plus 6. Do the following here. A. Sketch the root locus. B. Using a second order approximation, design the value of k to yield 10% overshoot for a unit step input. C. Estimate the settling time, peak time, rise time, and steady state error for the value of k. Design in B. While in D, determine the value of your second order approximation. Right now, we're going to present our solution. On our function, g of s is equals to k over s plus 2 times s plus 4 times s plus 6. As you can see, we have 3 poles here and 0 zeros. And we're going to use the angle formula, which is 2x plus 1 over p minus z times 180. We're going to use 0, 1, and 2 now as the value of x. Now we're going to substitute those values on our x. First is 0. So 2 times 0 plus 1 over 3 is equals to 60 degrees. That's your angle of asymptotes. Next is 2 times 1 plus 1 over 3. That's your second angle of asymptotes. Then for the third one, which is the 2 for the value of x, you will get 300 degrees for your angle of asymptotes. Next is we're going to find our centroid with the formula of summation of real p minus summation of real z over p minus z. Now, with our roots of our poles, we will minus negative 2 minus 4 minus 6 over 3 is equals to 4. Negative 4. That's your centroid of your root locus.
So after all that, we have gotten all our desired data. Now we are going to plot those data in our Cartesian plane. So as you can all see, the value of the poles, which is negative 6, negative 4, and negative 2, is marked with an X. Then, as we look, the centroid is in negative 4, and our 3 thetas, or our 3 angles, are found in 60 degrees, 180 degrees, and 300 degrees. So after all that, we put it in our graph. It will look like this. So for our breakaway point, we use the formula negative 1 over g of s. So as we plug in the data, we can see that negative 1 times s plus 2 times the quantity s plus 4 and s plus 6 makes up our g of s. So we didn't put the basic form because we moved directly to our working equation. So as we expand this, or as we multiplied or use FOIL method on all 3 equation, we come up with s cubed plus 12s squared plus 44s plus 48. So as we can see, we use the quadratic equation, which is negative b plus and minus square root of b squared minus 4ac all over 2a. So we plugged in the values and we got 2 breakaway points. The breakaway points are determined by the power of the highest power. So minus 1. So if the highest power is 3 minus 1, so 2. So we have 2 breakaway values, which is 5.155 and 2.845. So we also plug this into our graph. So for our question B, it is about solving for gain. So we must satisfy the condition, which is 10% overshoot. So in solving, we have to remember that, or we have to put in mind that the value of r to satisfy our condition will equal to 3.431. So for our first way of finding k, we have identified 2 ways of solving for k that satisfies the equation or the condition. So our first method is by combining the length of poles, which is just multiplying all the roots, which is 2, 4, and 6. So we get 48 minus r, or for the condition. So 48 minus 3.431 is equal to 44.56. Meanwhile, the other way or other method is used by by utilizing the characteristic equation, which is solved by multiplying all the roots. So equation of roots, which is s plus 2, s plus 4, and s plus 6. So as we multiply those three, we get s cubed plus 12s squared plus 44s plus 48. So we do the matrix form. So we listed s cubed, s squared, s to the power of 1, and s to the power of 0. So as we look here, s cubed has 1, s has 44, meanwhile s squared has 12 and 48. So we pivot. So in solving s to the power of 1, we pivot at 12 and we got 40. S to the power of 0, we pivot at 40, then we get 48. So we get here that at s to the power of 0, it is equal to 48. So we subtract r, then we get 44.56.